Well, hello, class. Nice to see all of you here today. Hi, Brian. Today, we have a couple of reminders. The first reminder is you have the PowerPoint due this week. So please make sure you get that to me this evening, along with the discussion forums. I was pleased to see more entries to the discussion forum. Next week, we have the current events. The current events is going to focus on natural disasters, coastal flooding, hurricanes, tsunamis, and then explaining it and relating that to ocean temperatures or tectonics in the case of tsunamis, but relating this to what we've covered in class. We've covered the currents and the temperatures in the ocean now. We've covered the tectonics. So basically, you're going to be relating some natural disasters, two articles, to what we have covered in class. Same format as usual, which everyone has got down pat by now. Your cover, 2 paragraphs per article, and then the separate literature cited page. So that would be one of the 2 things that are due next week. The second is the quiz. The quiz review is posted. We will be going over the quiz review Monday. Today, we're finishing up the material. Our next unit is marine biology. Next week in the marine biology, we will be watching videos that I have shot. One for a marine biology assignment, a virtual field trip that you guys will be going on. And then we'll be watching videos that I shot for the extra credit, which is marine biology based as well. So on Monday, we will be reviewing for the quiz that's due Wednesday. And we'll be watching a variety of marine biology local video shot that I shot with my daughter in preparation for virtual field trips that during the pandemic, I wanted to put together some creative ways to get students out in the field. And being we're kind of locked in class because this is not a field class, we will take advantage of those videos and use them. They fit really well in the marine biology program. So next week, we won't be doing PowerPoint lectures. We'll be visiting various locations in the area and looking at the marine environment there. So next week will kind of be an interesting and exciting week. And then the associated trip reports, one will be for credit and one will be for extra credit, a great way to earn 5 points added on to your final grade. So next week is kind of a exciting time, but almost as exciting. We have this week's wrap-up lecture. We are going to look at the coastal zone of the marine environment.
Professor, are you going to present the videos on a Zoom, or do we look them up on the computer?
Well, they are on the computer. Like everything else we do, I record it for those who unfortunately have to miss class or want to review. But we will watch them in class and then discuss and add to our knowledge base through a little group discussion after the video, maybe some background on it, reinforcing, maybe I said something a little quick on a video that I can go over or answer any questions. So we'll be doing it on the Zoom, but the recordings are there for you to watch as well.
Thank you.
You're welcome. So the last thing that we are looking at in this particular unit is the coastal zone, the coast. fairly obvious. What's the coast? Well, it's part of the land that adjoins the sea. Not as obvious as they're very dynamic, which means they're always changing. Uplift, coastal uplift is creating new mountains, uplifting coastal zones. This occurs on the west coast of the United States. Volcanic islands in the Caribbean, volcanic islands in the Pacific. So, in the news, the other type, the submerging coastline due to sea level rise is there. And a lot of our coastal cities will be threatened with floods. We are seeing and experiencing more coastal flooding than in our recent history. And that trend should continue. But that's not the only type of coastline that we have. We do have coastline that is being created by uplifting. And we call that emergent versus submergent coastline. So an emergent coastline is uplifted. A submergent coastline is we're losing the coastline. And of course, on the east coast of the United States, we're not having active plate tectonics and sea level is rising. We see more coastal flooding and we're experiencing submergent coastlines. But that's not the only type of coastline there are. The emergent is the buildup of these coastlines on active margins. So those are two features of the coast. I want to show you this little image here before we go into our next. There's two scenarios. The top scenario, you have different rock layers and the ocean. So you have more of a cliff. The lower one, you see you have a little lobster there showing you the water. You have a little whale here. And another one is the top view. You have different rock strata as well, but they are differential erosion. So you have the cove. It's not a cliff, this is flat, but you have your different areas. You can have coves and points due to different types of rocks. Some rocks are more resistant to erosion. Some rocks are less. So these are two scenarios that you can have on a coastline. You can have vertical change in your rock strata or horizontal change in your rock strata. So when you have, let me go back to the share. When you have vertical change to the rock strata, it's called a concordant coastline. A concordant coastline has the vertical change, so you tend to have a sea cliff and notches caused by erosion in those particular manners. The discordant coastline, you have horizontal change in the rock strata, and you get yourself a more jagged coastline with coves and points. So you can have a submergent and an emergent coastline. The east coast of the United States is more submergent. The west coast is more emergent. You can have a concordant versus a discordant coastline. If you've ever been to New England's rocky coastline, they have a lot of cliffs. A lot of the mansions are built on cliffs overlooking the sea. And in California, you have Pebble Beach and other rocky coastlines, and those tend to be concordant. Our areas, the nice beach, flat, a coastal plain behind that beach, that is more of a discordant coastline, where you don't have that vertical buildup of the rock strata. It's horizontal and rather level. So those are two distinct different types of coastlines, just based on different features that you're looking at. Now, in the news, we're talking about sea level rise, and sea levels are rising. Okay, about 18,000 years ago, we were coming to the end of what we call the Wisconsin glaciation period. During this time, the ice caps receded and sea level rose over 400 feet in a rather short time. Also during this time, humans were going through what we call the Neolithic Revolution. The Neolithic Revolution is the change in a lifestyle from a hunter-gatherer to a more agrarian or farming lifestyle where you have permanent settlements. And these permanent settlements were popping up on the coasts and on rivers because then there's water, there's fertile flat land. And so humans were going through a transition at this time as well. Well, as sea level rose over 400 feet in a short period of time, people in their history, in their folklore, recorded stories about floods. And, you know, I mean, here in America and the Judeo-Christian tradition that we're most familiar with, that story goes around Noah. But it's not the only story in human tradition that deals with floods. I mean, we've heard of Atlantis. The Minoan culture all but disappeared during this time. We can look at the ancient caves of Lascaux, France, where that cave art is from that Neolithic time. And most of those are underwater now, but the people that inhabited those caves, well, I mean, they didn't have gills, they didn't live underwater. So we know that sea level rose a great deal in a short period of time at the dawn of civilization. So the sea level rise kind of hit a lull. Now, since 1900, we've noticed the sea levels are rising again, and this is due to the retreat of the ice sheets on Greenland and on Antarctica. The North Pole is covered in ice. You know, we have the ice cap, the northern ice cap, and that does have a big bearing on climate because, you know, it changes ocean currents and it's cold. It's a big cold block of ice sitting on top of the world. But sea level wise, it has no bearing whatsoever because that ice is already in the water. So as sea levels rising today, it's only from Greenland. It's only from Antarctica, those glaciers that are receding. And there's also a small degree, but still a degree of what we call thermal expansion. As the temperature rises, water occupies a little more space. So since the 1900s, we have seen an increase in sea level. So we'll look at these charts here. In the past, you see, here's that huge spike in sea level at the end of the Wisconsin glaciation period. Now, we still are technically in an ice age. An ice age is anytime you have ice caps. But we're in an interglacial period, and that means the ice is really confined toward the poles. It's not covering most of the land like it was back at the peak of the Wisconsin glacial period. So sea level has been very stable now for near 8,000 years, but recently we've seen an incremental rise in sea level. Now, projections are all over the board. It's kind of like waiting for a hurricane because it's difficult to measure ice loss. I mean, you can measure it, look at a glacier and see, well, you know, it receded a quarter mile. But you really don't know what's happening under that ice because ice can be miles thick. So really, projections are just the best guess of computer models when you feed in the data. So we're all over the place. You know, we could see a 20 centimeter or 6-inch rise, we could see a 25-inch rise over the next 100 years or so. So really, we can't predict what the future has in store, but we do know that during the peak of the Wisconsin glacial period, and we'll use Florida as an example, this is what Florida looked like. So Florida was about 2/3 bigger when you look at the coast than it is today. Us here, we were center state. We were like a savanna. Florida, we had woolly mammoths and mastodons and giant cave bears and glyptodons, whole different class of organisms. We call them the megafauna. But due to climate change and possibly overhunting, we lost much of our megafauna. You know, the woolly mammoth stuff are extinct. I mean, there's still some pretty big animals elsewhere, but not to the extent that they were back during the peak of the glacial period. Now, if you're to project and you look at a 60-meter, which would mean we lose our ice caps, Florida could be mostly underwater. We know in geologic history, Florida has been totally underwater. During the age of the dinosaurs, 65 million years ago, Florida was a shallow sea. We are covered in limestone, evaporite, and fossiliferous, which means old coral reefs full of fossils. We also know that we were bigger at one time. One of my favorite dive sites back when I was a diver, I used to love to go to Venice. And Venice, which is only about an hour from here, is called the shark tooth capital of the world. And it is so much fun to go find megalodon teeth. And I found my fair share of megalodon teeth. But you also find horse teeth, mastodon teeth. I found a few mammoth and mastodon teeth fragments. You find giant manatee and associated dugong skeletal remains. So you find both land and marine specimens because Florida is oscillating, because we're at a pretty low, we're oscillating between dry land and shallow sea throughout our history. So it's very fascinating, the fossil history. There's a lot of great fossil beds in Florida. There's a lot of fantastic scuba dives, both through fossil beds in sinkholes and in springs, and coastal dives. You can find shark teeth in places like the Peace River. If you just comb the beaches in Venice, you can find a whole lot of smaller shark teeth, and the bigger ones, they're found a little offshore. But still, we know that Florida has a rich history based on sea level, tied to glaciers. Something that we fight every day, though, is coastal erosion. We talked about longshore current and, tides, even storm surges carve out the passes like Johns Pass and Hurricane Pass. Daily waves move sandbars around. And, living in a beach and a tourist-based industry, we're constantly battling the forces of nature and coastal erosion. Over time, jagged coastlines tend to be straightened out by coastal erosion. When we looked at dynamics of waves, we see they bend toward the shallows. So here on these concentrated points, you'll get more erosion, and they move away from the deeper areas where you'd get deposition. So over time, the natural order of things is to straighten out these jagged coastlines. Something we see here on the coastline is your high energy versus low energy coastlines. Let's just do a quick diagram of the an intercoastal area. Just draw a quick one, And then here, the east coast of the United States is characterized by what we call barrier islands. Okay, so barrier islands are giant sandbars that were deposited at the end of the last glacial period. So all the way up and down the coastline, here's the continents, and we have these long, huge sandbars. And these long, huge sandbars have what we call passes where the water flows in and out. Now on the Atlantic Ocean or Gulf, on the side, you have beaches because they're higher energy. Sand is a little larger sediment than silt, clay, and mud. So when you have a beach, the waves wash away the smaller sediments, leaving behind the heavier sand. We see our Gulf beaches have sand. If you go to the Atlantic, there's a little more wave action and the beaches are a little coarser. As you move up the East Coast and the waves get a little more, the sand gets coarser and coarser as well. On the interior of our barrier islands, you have more of a bay environment. Muds, sediments build up, salt marshes can grow, mangroves can take root, seagrasses can grow in these intracoastal areas because they're lower energy. And by energy, we mean there's less wave action, less turbulence. So in the quieter areas, you have muddier substrate. Substrate refers to the sediment. In areas with current, you have coarse substrate. And this totally affects what grows there. So a high energy coast, back to the slides, a high energy coast is frequently battered by waves. So there's more erosion, coarser sediments left behind, less deposition. A low energy coast generally only has the ebbs and flows of a gentle tide. You get more deposition, muddier environments, more rooted vegetation, and the associated organisms that live there. So high energy coasts, like around here, our Gulf beaches tend to be sandy. Lower energy coasts, like the intracoastals or a beach like Gulfport Beach or Apollo Beach, they tend to be muddier and have more rooted vegetation because the sediments are not as sandy. All in all, though, the beach is made of sediments. It's where we are on the coast. Most of the sediments are sand. These are all sizes of sediments. Cobbles are a little bigger than pebbles, bigger than gravel, bigger than sand. Then you get your silts and your muds, and they are found more in the bays and the mud flats. They're not really a beach. You wouldn't go throw a towel down on a mud flat and lay down. But sand is what most beaches are consisted of. Here, you can see this is more of a rocky beach, strong currents. So not all beaches are beautiful sand. This would be a rocky beach. This is found more in the colder water, a lot more turbulent. But our beaches are open coasts, which have, those are high energy beaches, and protected coasts are low energy beaches. But beaches all tend to have a similar profile. Your breaker zone carves a little notch, and on either side of the notch, you have longshore bars. This is called near shore, okay? Because it's near the shore, but it's always underwater. So our near shore environment has some sandbars. Once you pass that outer sandbar and you're past the breakers, it's called offshore. So our breaker zone is sandbars and where the waves break at half the wavelength of your typical wave. They are dynamic, so those sandbars may be different from day to day. When you get to your tide line, you have your low tide line and your high tide line. That's called the intertidal zone. Behind your high tide line is called the foreshore. That foreshore generally has a notch behind it where debris builds up. That debris is called the rack line with a W, rack line. And then behind that, you have your back shore. And then the end of the beach terminates with your dunes. And the dunes are basically plants mixed with mounds of sand. Dune plants are protected, generally speaking, by law. They're not necessarily endangered, but these dunes, the buildup of sand, helps prevent coastal flooding. We've made a lot of mistakes in the past as people. When we first settled our barrier islands, we cut down a lot of the dune plants and flattened the dunes because, hey, who wants to see dunes from a hotel when you can see the beach? Well, as a storm rolls in and that storm surge follows and you've lowered your sea level by 10, 12 feet, then you're asking for trouble. So dune plants are protected by law, not because they're rare, but because they're important. We've already discussed these parts. That drift line is the rack. Now, we are always fighting longshore currents. Remember, longshore currents is the general direction of the current due to prevailing winds. So our beaches drift. The beaches drift in the direction of the prevailing winds. So here's our depositional coast, east coast of the United States. We are typically barrier island. When you have any islands or anything, you get what's called a tombolo. We mimic these tombolos actually by building causeways. Causeways, we don't build them anymore. We maintain them because it's not cost effective to tear them down, but they really, really restrict tidal flow. So we're not really building them anymore. We build more of the bridges with openings for tides. But you see the sand spit, okay? This is always in the direction of longshore. You wouldn't have a sand spit the other way. Bays tend to close and open due to erosion. So everything's moving in the general direction of east, maybe a little bit southeast, east, southeast in this image, because, pardon me, the longshore current's moving in that direction. But all these are temporary environments, and we spend millions and millions of dollars fighting this deposition and erosion because we build the hotels and sell this beachfront as premium property. Here's an image of a sand spit. So the current is actually coming from the northwest, moving in this direction, and you can see the depositional feature being pushed in this way. So that is what we call a sand spit. Here's a bay mouth bar when the longshore builds up sandbars and you close off these bays. Remember, everything tends to straighten out. The barrier island. Here's your ocean or gulf. Here's your intracoastal. You can tell by, look, the mud flats. Here, beach, strong waves, low energy. We call it the intracoastal, but generally speaking, most books call it a lagoon. So here's your barrier island, and then here's your area. So let's have a look at it. On the ocean or gulf side, you have your beach. Behind the beach, you have your dunes. and then some scrub. At the crown of that barrier island, you have what we call the maritime forest. The maritime forest or hammock. As you move back down the barrier island toward the intracoastals, you wind up with a little more scrub. And then here it's called the Mangrove Fringe. Mangrove is the climax species. You'll also find salt marsh, which is a transition, and mud flats. When the tide is really low, you have expansive meadows of mud. The salt marsh species is Spartina, and Spartina traps mangrove propagules, and then the mangroves grow and fill in and are the climax community. Then you have the intracoastals, which is our estuaries. These are called bar-built estuaries, by the way, because this huge sandbar, which is the intercoastal itself, the island, allows runoff and tidal influx. So here's your estuary, and in the estuary, you get a variety of seagrasses. We have 3 main seagrasses in Tampa Bay. Estuaries are called the cradles of the ocean because almost 90% of ocean life enters estuaries to reproduce. Behind, when you come up, you have much the same habitat. You don't really get beaches, you get more of a salt marsh, mangrove zone, a little bit of a coastal plain behind there, which is your freshwater hammock. That freshwater hammock is still tied to the marine environment. And here we get the cypress or a willow marsh or something like that. And then you have your uplands again. So this is the structure of the barrier island. Our beaches on the Atlantic and Gulf coasts are on barrier islands. Darwin was the first to describe this phenomenon. Okay, here we have a subsidence. So you have your volcanic island. The volcano is extinct. It's in the tropics, so you have a reef growing on the island, coral reef, tropics, warm. There's 2 types of coral. The hermatypic coral. Hermatypic, Hermatypic, hermatypic. That's reef building coral. It has a symbiotic algae living in its tissue called zooxanthellae. Now the zooxanthellae, the dinoflagellate algae, needs warm water. So reef building coral only grows in warm, shallow water. We also have non-reef building coral, and that can grow anywhere, grow in deep water, it can grow in the dark, because it doesn't have algae living in its tissue. It doesn't form huge reefs like the reef building algae, but it does. So here we're looking at reef building. So it's got to be warm water, it's shallow. As the volcano subsides, sinks, you wind up having a atoll or a ring of coral, also called a blue hole. There's a very famous blue hole in the Atlantic called the Belize. Belize has a big blue hole, but there's several blue holes and atolls in the Caribbean. It's a phenomenon, though, we find very often in the Pacific because, you know, very active plate tectonics there. And this was first described by Charles Darwin as well. Some images of each. Here's a fringing reef on an active volcano. You can see how close it is. These places are great to visit. If you're a snorkel or a scuba diver, you just walk out of your hotel and, you know, 100 feet out, 100 yards out, you're in a coral reef looking at beautiful fish. Barrier reef, though, you have a lagoon or a intracoastal in between them because subsidence occurred. You got a big gap. And then lastly, your blue hole is left, your atoll. Another coastal feature is an estuary. And there's 4 major types of estuaries. Due to sea level rise in the not so distant past, 10 to 12,000 years ago, rivers have been inundated, and that's called a drowned river estuary. Glacial valleys have also been inundated, and those are called fjords. So drowned rivers where a river meets the sea, a fjords where a glacier met the sea. Our barrier islands, which we've learned about, those are called bar-built. And then the last are the tectonic coastlines, like San Francisco Bay or Puget Sound. So these are the different types of estuaries that we have. Areas where the water is brackish, which means a mix of fresh and salt water. Charleston, South Carolina, is a drowned river. Hillsborough River is a drowned river. Fjords can be thousands of feet, kilometer deep. Bar-built estuaries are what we're most familiar with. You got your sandbars and your intracoastals, and the runoff provides brackish water. And of course, tectonic, like San Francisco Bay or Puget Sound, are on active boundaries. Now remember, salt and fresh water have different densities. They don't mix. Salt water is heavier. So what we do is we have saltwater wedges moving in and out of estuaries. High tide, the wedge pushes up, and then low tide, it goes back. And I'm not necessarily interested in you memorizing the bottom topography and what happens. Just realize anything that lives in an estuary has to be able to deal with salt water and fresh water, because you're stuck with both conditions depending on the tide, depending on the weather. So the Pacific coast is a emerging coastline, rising margin, tectonic estuaries. The Atlantic coast is passive, so right now it's submerging, and it's dominated by either drowned rivers, because remember, the Ice Age left rivers like the Mississippi, the Hudson, or bar-built estuaries, because we have a barrier island system that moves all around the East Coast and the Gulf Coast. And then the Gulf Coast is just a mini Atlantic coast. Things that we do to help prevent erosion is we build groins. Groins stop that longshore current and trap the sand. Now, notice if the current is moving in this direction, a westerly direction from the east, the beaches build up on the east side of the groins. Here, we also build seawalls to block the incoming waves. But the most common thing we do is we bring sand in. We either pump it via barge or truck it in. And so we have to re-nourish beaches constantly. Okay, this is to show you here. Look, here's your jetty and your groin. The current has to be coming from the east, pushing west, because we're building up here. So you can tell which way current goes by observing where the sand is building up and where the erosion is taking place. Places like Miami Beach and beaches all around have extensive groin, jetty, and re-nourishment programs, because after all, humans have interfered with coastal processes throughout the entire United States. Well, that wraps up the unit of our coastlines and beach dynamics. Next week, we will review and we will watch marine biology videos shot locally. Tonight, you do have the PowerPoint that's due and the discussion forum that needs addressing. Are there any questions before I dismiss class? Well, thanks to everybody. Have a great weekend. I very much look forward to next week and watching videos and discussing local tall tales on our experiences with the coastline. Have a great weekend, all, and I look forward to seeing you next week.
Hey, Professor, this is Jalen.
Yes, Jalen.
I've done the PowerPoint and I've done the transition and animation to it. That's what you mean, right? Plus, yeah, I did. I also got 10 slides.
Okay, well, I mean, I will grade them and go over them when the assignment closes. So it'll take me a few days to go through them.
Okay.
Okay?
Yes.
Very good.
Okay. Thank you.
Have a great weekend.
You too.
Bye now.
Bye now.
Hey, Professor, this is Artesia.
Hi.
Hi, I was wondering why we restore our coastlines. I mean, is that just to preserve our current way of life? I mean,
Yes.
would it?
Yeah.
Okay.
I mean, you can't really open up a beach bar without a beach.
Gotcha. So what would happen if we didn't?
Well, the economy in Florida would collapse because we're a tourism economy. We'd all have to move inland.
Okay, so it would just, I mean, so slowly just the edges of Florida would erode?
Oh, yeah. I mean, our beaches are constantly moving, so you wouldn't be able to, it would have to be like Fort DeSoto, all the beaches, where you just let it happen naturally, but you didn't have any structures.
Oh, I don't know what Fort DeSoto's like. Could you describe what it looks like?
It looks like no real buildings.
Oh, okay.
The beaches are eroding. They're changing all the time. You got dunes, intercoastals. So we'll be watching some videos on Fort DeSoto next week.
Okay, cool.
Okay.
Thanks, that was it. Have a good weekend.
No problem. You have a good weekend as well.